Thank you all for coming to this second lecture. So what I'll be telling you about today will be joint work with Adam Marcus, who's sitting back there, and Nikhil Srivastava, who's now at Berkeley. So the Kadison, did that work? Yes. So the Kadison-Singer problem has many equivalent formulations and was equivalent to many other conjectures. So the ones that I will talk about a little bit will be Anderson's paving conjecture. There are others that I won't talk about, like the Bourgain-Tzafriri conjecture, the Feichtinger Conjecture. The main ones that I'm going to focus on that imply it are something called Ackermann and Anderson's paving conjecture and a conjecture of Weaver's called KS2, where the KS stands for Kadison-Singer. It was essentially designed to be an intelligible conjecture, or at least intelligible to people like me, that happen to imply the Kadison-Singer problem. So, and that was very useful because the original statement of the Kadison-Singer problem is really not intelligible to people like me, or me anyway, but I can state it for you. So what I'm really going to do is I'm going to tell you how we prove Weaver's conjecture, which implies Ackermann and Anderson's paving conjecture. And then at the very end, I'll mention a little bit about Anderson's paving conjecture and how we prove that directly as well, if we like. So the Kadison-Singer problem, for those who know, will probably be happy to see a statement of this form. They consider the space of bounded linear operators on L2n and take a look at what people call a massa, a maximum abelian subalgebra. And the conjecture said that if you have a pure state in the massa, then it has a unique, or sorry, it wasn't a conjecture. Really, the problem was, is the extension to the bigger space unique? And if we want to talk, they didn't actually conjecture whether the answer was yes or no, but we will establish that the answer is yes. Now again, for me, this is not a natural problem to the sort of mathematics I do. I often describe this as this is like trying to understand what a dog is by looking up the definition in a dictionary. It doesn't tell me anything, I can understand the words, but it doesn't tell me anything about how a dog will behave. So what I'm instead going to do is I'm going to introduce you to the animals that I know. So my pets, which really are things like matrices. So here's Anderson's paving conjecture. It considers a matrix. In this case, well, Hermitian, you may as well think symmetric, that's fine. Having the complexes involved doesn't really change the problem substantially. And it concerns partitions of the rows and columns of the matrix. So here I imagine I've partitioned the rows and columns into 3 different blocks. They don't have to be contiguous, I just drew it that way because it's nice. Take any partition of the rows and columns, and the question is, if this matrix A has zeros on the diagonal, does there exist a partition like this so that the norm of each block is substantially smaller than the norm of the original matrix A? So this would be the block, and that would be the matrix A. And to remind people, the matrix norm is just the maximum over all unit vectors of the norm of A times X, or if you like, the maximum absolute value of an eigenvalue in the symmetric case. So it's a measure of how much the matrix blows up vectors. Okay, so Anderson's paving conjecture was that however small you would like the blocks to be for any epsilon, there is a partition into a finite number of sets, k different sets, so that each of these blocks will have norm less than or equal to epsilon times the norm of the original. Now, what's important for this problem is that epsilon and k should be constants independent of the dimension. And the reason, or I guess one way to think this might be sort of reasonable is at least if you have zeros on the diagonals, and well, if you just gave me only the diagonals, those would all be blocks of 0 norm. The question is, if you don't go quite to the diagonal blocks, you can still take constant fractions. Can you get small norm in each of those blocks? Okay, this is closer to the sort of thing I understand. We're going to get a little more concrete in a moment, but I will tell you that Anderson's conjecture in this nice finite dimensional statement, from that, it's very easy to go into an infinite dimensional statement, where instead now you have bounded self-adjoint operators on L2, and then you want to partition the coordinates again into k subsets so that the operator norms in each of the blocks are less than or equal to epsilon times the operator norm of the original. So from this For those who are familiar with such things, it's not too hard to get to Kadison-Singer. And and from this statement about finite dimensional matrices, it's not too hard to go to the infinite dimensional one. Okay, that said, we're only going to return to this at the end. I'm going to begin by dealing with the most concrete version of this problem I know, and that's the one we're going to attack, and that is Weaver's conjecture. So Weaver's conjecture concerns what I will call moments of a collection of vectors. So imagine you have a couple of vectors in some d-dimensional space. Here I drew two. Let me tell you what their moments are in the direction of a unit vector u. I'm hoping that u is visible. It looks a little faint up there. So I'd say the moment in direction u is the sum of the squares of the inner products of u with the vectors. So if I just have two vectors, say v1 is length 1 and orthogonal to it I have v2 of length 2, if I go in the direction of v1, the moment will be 1. If we go in the direction, if u points in the direction of v2, the moment will be 4 in that direction, and halfway in between it turns out to be 2.5. Okay, so this is how I describe the moments of a collection of vectors. What we're going to be interested in is collections of vectors where the moments are spherical, where in every single direction you get the same thing. So in order to define that and see what it means, let's first just understand how we can write out what the moments are. The sum of squares is a nice expression. If you want, you can multiply by vi transpose times u on the other side, or multiply by the transpose, and you get basically the moments become a quadratic form. So if I take those sets of vectors, I sum their outer products with themselves, I'll get a matrix. And then the moment in direction u is just u transpose times that matrix times u. Okay, so if my vectors have spherical moments, the way I'm going to draw this to help me think about it geometrically is I think of my vectors as being like a generalization of jacks, like those toys you throw up in the air and try to pick up without hurting yourself while you're catching a ball. And I'm actually going to draw for every vector minus the vector, because since I'm taking squares, it really doesn't matter. And it helps me see that when I have vectors where all the moments are the same in every direction, it's a nice, well-balanced sort of spherical object. You can think about it, says the moments of inertia, if you were to try spinning it, are also the same in every single direction. It's equally easy to spin in any direction. Okay, so if we have spherical moments, that's the same as saying that the sum of the outer products of the vectors with themselves is the identity matrix. And this is also called isotropic position and has many, many different names in different disciplines. But it's a very nicely balanced set of vectors. And the question that Weaver asks is about when can you take such a set of vectors and partition them into two sets so that each set is approximately half spherical. So you might say I took two of the vectors, put them here. I took the other two vectors, put them here. And both of these, we'll say, are sort of approximately half spherical, where for now I'll say it's half spherical if all of the moments are between 1/4 and 3/4. 1/4 and 3/4 isn't magical, but anything really would sort of near a half would be fine. But for sake of argument, let's think of between 1/4 and 3/4 for both sets. So let's say I make this one set S1 and this one S2. We want all the moments in each set to be at between 1/4 and 3/4. This is equivalent to saying that if I take the sum of the outer products of the vectors in each set, all the eigenvalues of the resulting matrix should be between 1/4 and 3/4. And because I'm dividing into two sets, and this is specific for two, it's equivalent to just actually say that all the eigenvalues in each set are less than or equal to 3/4, because one is the complement of the other. So if S1 has an eigenvalue less than 3/4, if it has a short direction, then S2 has to have a corresponding big direction. So really the question becomes, can I partition my sets of vectors into two sets so that the largest eigenvalue of the sum of the outer products in each set is less than 3/4? And that's also equivalent to looking at the matrix norm. Okay, so the question is, can you do this? Or when can you do it? There's one obvious obstacle. What if some of your vectors are really big? So like in this case, if I have two really big vectors, we're going to have a problem. Because if I put just one of the really big vectors in one set and one of the other really big vectors in another set, my moments are not at all spherical. They're highly skewed. So a big vector is a problem. I mean, the other way you could think about dividing them up is put both of the big vectors in one set. then both of these are spherical in this case, but they're not half spherical. I want the moments to be about a half, and in this case, the moments are about 1. In this case, they're teeny. Okay, so big vectors are an obvious obstruction. Weaver's conjecture is that those are the only obstruction. So Weaver's conjecture, KS2, was that there's some positive constants, alpha and epsilon, so that if all the vectors have squared norms less than alpha, so, okay, I said big is an obstacle. We'll define big as anything more than alpha. Then you can partition them into 2 parts so that the sums of the eigenvalues of the sums of the outer products of vectors in each part are, okay, Weaver conjecture bounded away from 1. I was saying half spherical, so, I had an epsilon of a 4th here. But Weaver's conjecture just was bounded away from 1. And Weaver showed that implies the Ackermann and Anderson's paving conjecture. And Ackermann and Anderson have a monograph which shows that their paving conjecture implies the Kadison-Singer conjecture. So for me, this was very, very nice. This translates a problem to something that, to me, is very, very concrete and that I can think about. And I will show you, or I'll try to explain also why we had some hope based on the previous lecture to believe that this should be true. Well, in the previous lecture, I tried as well. So we're going to prove a strong version of this theorem. What we prove actually is that for any alpha you want, upper bound on the norms of the vectors, so the vectors are all small, then there's a partition into 2 parts where we can get as close to half spherical as we want by making alpha smaller. So we will get all of the eigenvalues in each part are most a half plus 3 root alpha. The constant we have is a little less than 3, but 3 is good to say now, because it was more than 2, although I think Adam has a recent paper that might get it under 2. Anyway, we're not to the tight bound yet. That'll be a conjecture at the end of the talk. So this is the main thing I want to tell you how we prove. Let's see, do I want the next slide yet? No. So just to emphasize, we're going to prove this simple statement that we have a bunch of vectors in isotropic position if all of their norms are small. And the important point is that this alpha is independent of the dimension. If alpha depended on the dimension, it's not too hard. We need a constant alpha that's independent of the dimension. Then you can partition them into 2 halves so that all of the eigenvalues in each part are really pretty close to a half. Okay, this is a good point for questions, because this is what I'm going to tell you how we prove for the next 45 minutes or so. Okay, good. So the first thing you should try when you look at a problem like this is, what about a random partition? And it almost works. So there's a field of study of people doing random matrix theory these days, doing things like they call proving matrix Chernoff bounds, matrix Bernstein bounds, the bounds for concentrations of random matrices, using one of them by Trop, which is a variant of Rudelson's matrix Chernoff bound. You can say that a random partition works if all of the vectors have squared norms less than or equal to 1 over the log of the dimension. So this is not a constant independent of the dimension, but it's a good sanity check. On the other hand, random partitions can fail. There's a very easy example on which a random partition fails. That is, what if my configuration just involves taking standard coordinate vectors, the standard basis, but repeated a couple of times? So take, say, if I want to have norm squared alpha, then I will have 1 over alpha copies of each standard basis vector. And if I take that example, imagine what happens when I take a random partition of that. You can think of then coloring each of those vectors blue or green. There is some chance that I will wind up in one of my partitions having all of the vectors pointing in one direction. So I could have like all of the vectors in this direction colored blue. The probability is not that high. The probability is about 2 to the minus the number of vectors pointing in one direction. But if I'm keeping alpha fixed as the dimension grows, then probably it's going to happen for one of the directions. So the chance that it doesn't happen, or the chance that all of the there's some direction in which all the vectors get put in the same partition approaches 1. Okay, this doesn't mean you need to give up. It says a random partition at least is probably bad. in this example. Of course, this is a very easy example. You know what to do in this example. You take half the vectors in each direction, and you put them in one set, and the other half, you put them in the other set. Okay, so here's a related example, and this sort of gives us more hope that random, even if it usually fails, shouldn't be bad. It comes from expander graphs. So here's how we will take an expander graph and make a configuration of vectors. So if I have an expander graph with n vertices and m edges, for each edge I make a vector. Okay, my coordinates are indexed by the vertices. And for each edge I make a vector that is 1 at one of its endpoints, one vertex, and -1 at the other endpoint. These are the same vectors I associated with edges last lecture. And if you take a look at the sums of the outer products of those vectors, they give you the Laplacian matrix of the graph. And if the graph is an expander, and we know good expanders exist, then it's not exactly spherical, but they're very close to spherical. It's very close to isotropic position. And you could make a small perturbation to the vectors now and put them in isotropic position. And then you can ask, if I give you such an expander graph, or for these examples, the Kadison-Singer problem becomes, can I partition the edges of my expander graph into two sets, such that both of those sets are expanders themselves? So it's like I take a graph, I take the edges, I partition it into two graphs, where each edge can only appear in one graph. The answer is yes. So this was proved. There are two different constructions, one by Broder, Friese, and Upfall, the other by Friese and Malloy. And basically what they do in their analyses of this is they consider a random partition with some constraints, but basically a random partition. It usually fails, but they use a technique in probabilistic combinatorics called the Lovász local lemma to prove that the probability it fails is non-zero. Sorry, the probability it succeeds is non-zero. The probability it fails is strictly less than 1. So even though this almost always fails, they can prove with a random partition there is a non-zero probability it succeeds. And then you know the partition exists. So if you know there is a non-zero probability something exists, it exists. And you don't have to worry about it anymore. So there's hope. So we won't give up on randomness. Okay, so now let me tell you what we're going to prove. I'm going to restate it to make it a little cleaner. I have these two matrices. I want to partition S1 and S2, and we have these two matrices, the sum of outer products in S1 and the sum of outer products of vectors in S2. I'm going to put them all in one big matrix and put a block of zeros up here and a block of zeros down there. So there should be a block matrix now. So I have one matrix up here, the other matrix down there, and of course the eigenvalues of this entire matrix are just the union of the eigenvalues of these two diagonal blocks. So really what I want to do is I want to take this one big matrix and prove to you that the eigenvalues in this one big matrix, once I choose S1 and S2 correctly, are less than or equal to half plus 3 root alpha. Now to do that, we're going to do something which doesn't look like much of a change. I'm going to remember that the eigenvalues are the roots of the characteristic polynomial. So when I write the polynomial of something, I mean the characteristic polynomial of this matrix. So that's what we want to prove. And what we're going to do is we're going to prove this by studying what happens when we take a random partition. But when we take the random partition, we're going to look at the expected characteristic polynomial that we get out from a random partition. Now, by the way, I should warn you, this looks like a mistake. Actually, had we been smarter, we probably would have realized this was a mistake and not pursued it. But it turns out that it works by some sort of miracle. So, and I'll explain why in a few minutes. It looks like a mistake if you don't see it yet. So what we're going to do is first we're going to prove that this expected characteristic polynomial has real roots. So it's a very nice polynomial. Now, of course, you know that each of the characteristic polynomial of any symmetric matrix has real roots. But we're showing that when you take a look at the average of them, over this particular family of polynomials, it will have real roots. That sort of thing is not true in general. Then we're going to actually, or at the very end of the talk, we'll actually analyze what is the largest root of this expected characteristic polynomial. And you will see that it is actually exactly the bound we want. It's 1/2 plus 3 root alpha. And the reason that will enable us to conclude that a good partition exists is it turns out that our family of polynomials we're studying is a very nice family of polynomials. We call it an interlacing family. And I will define what that is. But what happens when you have a set of polynomials that is an interlacing family? There is always some polynomial in the family whose largest root is less than or equal to the largest root of the average. There might be only one, but there is at least one. And what that means for us is there is some partition such that the largest eigenvalue of each of those matrices is at most this largest root of the average, which was a half plus 3 root alpha. So because it's an interlacing family, we are able to prove a theorem about the average and conclude something about an individual member in the family. OK, so let's take a look a little more at this expected characteristic polynomial. I want to introduce a little notation. So what we're doing, again, is that I'm putting each vector in a set, S1 or S2. The way I'll indicate that is for my n vectors, I'll write down numbers sigma 1 through sigma n. So sigma I is equal to 1 if the ith vector is in set 1, and sigma I is equal to 2 if the ith vector is in set 2. That's how I'll keep track of the sets. And then my individual polynomials that I'm going to be averaging over, I'll index. I'll call p sigma 1 through sigma n is just the polynomial where I put all the vectors where sigma I equals 1 in the upper block and the others where sigma I equals 2 in the lower block. So once I introduce that notation, I can simplify things a little bit more. It means I can actually talk about choosing one of two vectors. So if I want vi to be in the upper block, it means I can make a vector which I'll think of as vi on the top and 0 down below. And if I want vi in the lower block, I put a block of zeros up top and vi down below. And I'm going to define those vectors I call ai. And those are dependent on sigma I. So now this block matrix I had, I can now write as the sum of ai times their transposes. It's just a more compact way of writing things, but it will be useful. So now we're going to generalize a bit. I told you I want to look at the average polynomial. So we're going to look at something we call the mixed characteristic polynomial. And I'll explain why we choose that name in a moment. That we define, if I have a1 through an are independently chosen random vectors, not identically distributed. Each can have their own distribution. In our case, they will. But if I have a bunch of independently chosen random vectors, I will look at the expected characteristic polynomial of the sum of the vectors times their conjugates, or transposes. Well, OK. We need to do this for theorems over the complexes, but it turns out everything you can do over the reals, and it's the same proof. So I'll probably usually say transpose, because it's easier to think about. OK, we call this the mixed characteristic polynomial. One thing we prove about it is that the mixed characteristic polynomial only depends on the covariances of the distributions of the vectors. So that means if I look at the expectations of the AI transposes, I call that a matrix capital AI. This polynomial actually only depends on those, this expected characteristic polynomial. That is a function of the fact that the AIs are independent. And just to remind you, my AIs, as you can imagine, are going to be this vector with probability 1/2 and this vector with probability 1/2. OK, so for that reason, I'm going to stop talking about distributions or something, or random vectors. I really just have to write down the covariances, and we will denote the mixed characteristic polynomial mu of a1 through an, where a1 through an are, again, the expectations of the outer products of the random vectors. Yes? Yes, so this is a polynomial and a variable x, which I have not bothered to write down. Yes. Yeah, so that will be a polynomial. OK, and just to fix, for some people, if they're trying to follow closely, the normalizations of everything now, the trace of my matrix AI is the trace of the expectation of the outer product, and expectation commutes with trace. So it's the expected trace of the outer product of AI with itself, which is the expected squared norm of the AIs. So my matrix capital AI has a trace at most alpha if these had squared norms at most alpha, which was sort of my condition on the vectors vi. Remember, I had my condition that my initial vectors vi had squared norms at most alpha. And also, the sum of my matrices AI is now 1/2 times the identity. It should have been the identity if we were in isotropic position, but now I've sort of taken my matrix and put it in an upper block and a lower block, each with probability 1/2. So we're doubling the dimensions. We're spreading it out. It's about 1/2 times the identity. At some point, I'm going to rescale things to make that identity, because it'll make some theorems cleaner. OK. The reason we called this the mixed characteristic polynomial is the constant term in this polynomial is a well-known object. It's called the mixed discriminant of a collection of matrices. And there's been a lot of work on the mixed discriminant, and we will leverage some of it. So actually, there's another particular case, which is very useful. It's in the case when my matrices AI are all diagonals. I mean, we can define this mixed characteristic polynomial, for all sorts of things. It doesn't have to be our distribution that I was looking at, and we will reason about it in general. So if the matrices AI are all diagonal, and we take a look at the mixed discriminant, it turns out to be the permanent of the matrix that you get by taking these diagonals and putting them in the columns of a matrix. So there's a relation to the permanent. And that relation is important to us. So there was a conjecture called van der Waarden's conjecture, which is about how small can the permanent of a doubly stochastic matrix be. In our world, van der Waarden's conjecture becomes the assertion that if I have a bunch of matrices of trace 1 that are diagonal, if I have diagonal matrices of trace 1, and their sum is the identity, then the constant term, or the mixed discriminant, is minimized if the matrices are all exactly multiples of the identity. So that would have been van der Waarden's conjecture about the permanent translated to mixed discriminants. And this was proved. There's a fairly complicated proofs by Agorichev and Falakman. What we're really motivated by is by a simpler proof of this theorem due to Gurvitz. Though if you really want to understand the simplicity of it, you read instead the write-up by Laurent and Scriver, as opposed to Gurvitz's original paper. It's an algebraic proof, and I will show you some of the techniques we use to prove it. OK. Gurvitz also proved a generalization of van der Waarden's conjecture. It was a conjecture of Boppet. He said, what if we just remove the restriction that the AIs be diagonal? He said the lower bound should be the same. So Boppet conjectured if I have positive semi-definite matrices of, Hermitian? Now I'm trying to remember if we need positive semi-definite. Probably. Yeah, OK, where all the traces are 1, and their sum is the identity, then the mixed discriminant should be minimized. Again, when all of them are diagonal. So that should be the limiting case. And Gurvitz also gave a simpler, Gurvitz gave a proof of this. He gave 2 proofs of it. It's his second, later, simpler proof that's going to motivate us a lot. OK, so the main technique we learned from Gurvitz was introducing real stable polynomials. So far, I've been talking about expected polynomials in one variable. The way we are going to prove this theorem is actually by deriving those polynomials from polynomials in many variables. But we need to generalize real rootedness. So the way we do that is we recall, at least if you have a polynomial with real coefficients in one variable, that the complex roots come in conjugate pairs, one with positive and one with negative imaginary part. So one way of saying that a polynomial is real rooted, if it has real coefficients, is just saying that it doesn't have any roots with positive complex part. And that would imply it's real rooted. That's what we generalize, to generalize the notion of real rootedness to multivariate polynomials. So you can say that a polynomial is real stable. It's a polynomial now in many variables, if it doesn't have any roots where every single variable has a positive complex part. So I wrote this as saying it has no roots in the upper half plane, but really it's the intersection of the upper half planes in every single variable. Doesn't have any roots. OK, so this is the generalization that we will use of real rootedness to multivariate polynomials. It has many, many nice properties. Some of them pop up also. This is sort of isomorphic to Garding's theory of hyperbolic polynomials. And the translation is useful sometimes. And this was used by Gurvitz in his nicer proofs of the van der Waarden conjecture and Boppet's conjecture. And that's what we're going to build on. So I'll just tell you a few things about real stable polynomials. Oh, also I want to say, if you want to learn more about them, there's some great surveys by David Wagner and by Robin P. Mantle. I think P. Mantle's talks about hyperbolic polynomials, but again, they're basically the same. So here's one very nice family of real stable polynomials. If you take positive semi-definite matrices A1 through AN, and sum them in variables. So we put z1 times a1 through zn times an, sum them together, take the determinant. That's a real stable polynomial. Okay, the first place I know this written down was this paper of Bourgain and Brandon. I think it was probably known before then. But anyway, it's a very easy thing to prove. Oh, no, okay. So I should say that strictly positive definite is easy. Positive semi-definite you can prove as long as there's no vector that's in the common null space.
Okay, that's fine.
Yes, okay, yeah. And that you sort of take a limit of the positive definite matrices to get that. Okay, here's the other theorem we want about real stable polynomials. If you take a real stable polynomial and subtract off the derivative in one of the variables, it's essentially a theorem of Lieb-Sokol, though they have it rotated 90 degrees from the theorem I'm stating here, that preserves real stability. So what we have now is we have an operation, we have a family of real stable polynomials, and I've given you an operation that preserves real stability. And finally, the last fact I want about real stable polynomials, if I take all the variables and I make them the same, take all the zi's, make them x, that's now a polynomial in just one variable. That is real stable. And in particular, that will be real rooted because it's a real stable polynomial in only one variable. Okay, this is all we need to prove that the mixed characteristic polynomials are real rooted, or the expected characteristic polynomials we derive. And when I say this is all you need, it's because there's a very, very simple formula for the mixed characteristic polynomial. It turns out the mixed characteristic polynomial is equal to what we do is we take those matrices A1 through A, and those were the expectations of the outer products of our random vectors of themselves. Take the sum of those in variables we introduce z1 through zn. Take the determinant. I told you that that is a real stable polynomial. We then subtract off the derivative in each of the variables. We apply that operator for each variable. So subtract off the derivative in the first variable, then apply subtracting off the derivative in the second variable, and so on. And then finally, when you're done, make all the variables the same and equal to x. That turns out to be the mixed characteristic polynomial. I won't prove it for you because it's an identity. And once you know that it's true, you can prove it. Although I will admit, our first proof of it was sort of ugly. People sent us simpler proofs. Because, and we, of course, knew it was true because we actually computed it symbolically. And that's how we knew it was true, right? If it comes out true on a couple small examples, it must be true, and then you find a proof. OK, so that's how we know the mixed characteristic polynomial is real rooted. And you'll find that actually, in combinatorics, there are many nice families of polynomials where when you take their average, for some reason, sometimes this, sometimes other, they turn out to be real rooted. So it's not completely unexpected that something like that may happen. Yes? I do not think it leads to a simpler proof. Well, OK, let me take that back. Bourgain and Brandon have some proofs of it in their work on real stable polynomials that build on this, and some generalizations. Some of them are probably easier than the original, but I'm not sure, because I only read the papers of Bourgain and Brandon and not the original. So they have a long list of papers on real stable polynomials in which they prove a lot of properties of them. OK, so that's real rootedness. Now I need to tell you about interlacing. I need to tell you what is an interlacing family and how do we prove our polynomials fit into one. So first, when do two polynomials interlace? It's when their roots alternate, when they do this. Think about a polynomial, a real rooted polynomial and its derivative. The roots of the derivative lie between the roots of the original. What we are actually going to be interested in is when polynomials have a common interlacing. So that is when I have two polynomials, say P1 and P2. Those are these blue curves. And there is another polynomial whose roots are these betas that interlaces both of them. So another way of saying this property for P1 and P2 to have a common interlacing is it means that if I take a look at these betas, the roots of the polynomial that interlaces both of them, and I can use those to divide the real line into segments, such that both P1 and P2 have exactly one root in each of these segments. OK, so the great property of polynomials that have a common interlacing, for our purposes, is that if two polynomials have a common interlacing, and I take a look at the largest root of their average, which is, say, right here, one of the polynomials has a smaller largest root. I mean, you can see it. I drew it right here. But the proof is easy. I mean, if I just have those two polynomials, you know that they both only have one root past this point. So you know that one of them is positive here and one is negative here. And the one that's positive there, well, its largest root had to be smaller. OK, so if two polynomials have a common interlacing, then the largest root of one of them is less than the largest root of the average. Actually, this fact I'm going to use so much, I want to remind you it's not always true. So let's just remember that if I've got two polynomials with real roots, their average might have no real roots. So even if they have real roots, the average doesn't have to be real rooted. Even if the average is real rooted, I don't know if you can tell. So these two polynomials don't interlace. Their average is real rooted, but its largest root is smaller than the largest root of both of these. So the average being real rooted doesn't really get you anything. For the sort of theorem we want, where we want the largest root of one of our polynomials to be less than the largest root of the average, OK, we don't actually need interlacing. We just need the fact that both of our polynomials have one root, and exactly one root after some point. But interlacing is a very convenient way to get that fact. So one reason interlacing is so convenient is there's a very nice characterization of when two polynomials have a common interlacing. So we know that two real-rooted polynomials have a common interlacing if and only if all convex combinations of them are real-rooted. So in particular, this is if and only if whenever I take lambda times p1 plus 1 minus lambda p2, where both of those coefficients should be positive. If all of those polynomials are real-rooted, that tells me the two polynomials have a common interlacing. OK, it's if and only if I'm going to use the if direction, or implies direction. We will show. So what's nice for me about this is it means that I can prove that two polynomials have a common interlacing by proving that their average, that all their averages are real-rooted. And as I showed you, we have a lot of techniques for proving that polynomials are real-rooted. OK, so now I can tell you what an interlacing family is. Because all of our polynomials are not going to have a common interlacing. That would be too much to hope for. But they do form an interlacing family. So in our interlacing family, what we're doing is we're writing our polynomials in our family on the leaves of a tree. And at every node higher up in the tree, we write the average of the polynomials beneath it. So the top node of the tree, I don't want to say root because we're also talking about roots of polynomials. The top node of the tree is the average of all of the polynomials at the leaves. OK, we say that these polynomials are an interlacing family if each pair of siblings has a common interlacing. Meaning these two nodes, say p21 and p22, they have to have a common interlacing. And these two nodes, the polynomial here and the polynomial here, they have to have a common interlacing. That's what we mean for our polynomials to be a common interlacing. So to simplify notation, you'll see what I've done here. You can do this more generally, but what I've done is I've indexed my polynomials by a string in sigma, in which the coordinates are all 1 or 2. I'm just going to write the prefix that's fixed in each of them. So like the polynomials under p1 are those that begin with 1, the second coordinate varies. The top node in the tree I'll call p empty set, because you don't fix anything, and it's the average of all of them. So what you can see is that when you have an interlacing family, there is always some leaf whose largest root is less than or equal to the largest root of the largest zero of the node at the top of the tree. And the proof is really trivial. Let me go back. So the way to see it is we know, say, that p1 and p2 have a common interlacing, and their average is p0. So I apply our previous theorem. It means that either p1 or p2's largest root is less than the largest root of the node at the top. So OK, let's say it's p1. You go down to that one. Then you know that these two have a common interlacing, and their average is p1. So one of them has a largest 0 that's less than the largest 0 of their average. So you just take the theorem that I showed you earlier about polynomials with a common interlacing and apply it inductively down the tree, and it lets you walk down the tree. So then you know that if your polynomials all form an interlacing family, there is always some one of them whose largest 0 is less than the largest 0 at the top of the tree. OK, so now I need to prove that my polynomials form an interlacing family. And then, okay, eventually we need to prove a bound on their largest roots. But let's prove they're an interlacing family. So recall the way I was choosing my polynomials is I indexed them by sigma 1 through sigma n, where sigma I tells me whether or not the ith vector goes in the upper block or the lower block. And then what I will do is I will consider fixing where vectors go one at a time. So for example, P1, if I just specify sigma 1 through sigma k, the polynomial P sigma 1 through sigma k, I get by fixing sigma 1 through sigma k and choosing the others at random. So fix the sets for the first k vectors, and the others you pick at random with probability 50-50. So I need to show that's an interlacing family. That means I need to take a look at two siblings in the tree. So two siblings in the tree are something like I fixed where the first k vectors go, and then I fixed the k plus first vector to go either in set 1 or set 2. And the other vectors are chosen at random, which set they go into. Those are two siblings in the tree, and I need to prove that those two expected characteristic polynomials have a common interlacing, which I prove by showing that any convex combination of them is real-rooted. And we do that by observing that this polynomial is actually a mixed characteristic polynomial. It's the mixed characteristic polynomial. You'll get the distribution is sigma k plus 2 through sigma n are 1 or 2 with probability 50-50, so they're uniform. Sigma 1 through sigma k, the first k choices are just fixed, constant. There's no randomness. That doesn't hurt. And the kth choice, we just make it 1 with probability lambda and 2 with probability 1 minus lambda. So you get a mixed characteristic polynomial from any average. And I already proved to you that mixed characteristic polynomials were real-rooted. Actually, this is why it was very important to us to handle the generalization of mixed characteristic polynomials rather than just the particular polynomials we had. It turns out there were other ways to prove that family was real-rooted. And this isn't much of a generalization, but it's a slight generalization. OK, so that actually ends this part of the proof. This tells me that my family of polynomials is an interlacing family. Therefore, if I can prove an upper bound on the maximum root of the polynomial at the top of the tree, there is a polynomial at the bottom whose largest root is smaller, or at most is big. And therefore, in our case, there will be a partition of our vectors into two sets that lets us prove the Weaver's conjecture. Yeah?
So do you use the multivariate real stable, or is it just single variable?
Oh, these are single variable polynomials, but the way we prove this is real-rooted is by going through the multivariate real stable. So this is a univariate polynomial, but the way we proved that it was real-rooted was by taking the multivariate generalization of it. And that was the proof I did before, really, for mixed characteristic polynomials. OK, so the last thing we need to do, which was many years of work, it turned out. What I just showed you actually was the easy part. That was year 1, is get an upper bound on the roots of these mixed characteristic polynomials. That turned out to be the hard part here. So here's a good normalization for stating this. Let's say I have a bunch of matrices, so their sum is the identity, and the traces of the individual matrices are at most epsilon. Then I will prove to you now, then this is what we needed to show, something like this, that the maximum root of the mixed characteristic polynomial is at most the square of 1 plus root epsilon. So, by the way, I should mention, under this normalization, all we needed was any bound less than 2. That would have sufficed to get Kadison-Singer and Weaver's conjecture. Getting it close to 1 is what lets us get the particularly sharp bounds like half-spherical sets. So the way we prove this is it turns out we again go through this characterization of the polynomial, or this definition of it that we use in this way of deriving it from a multivariate real stable polynomial. And we're going to reason about where the roots are of this multivariate polynomial in order to get eventually reasoning about where the roots are of the polynomial in one variable. So to begin this, what we need now is a notion of an upper bound on the roots of a multivariate polynomial. You know, if I have a univariate polynomial, you know what an upper bound is. Okay, at least, you know, if it's real rooted, it's the largest root. We need something to do that. We need an analog of that for multivariate polynomials. So we will say that W, a vector W, is an upper bound if it's, if the polynomial is positive there, and at all points bigger than W. If you increase any of the coordinates, you don't have any roots. So if you take the orthant rooted at W, we need that the polynomial has no roots there. And you can do, there are always upper bounds for real stable polynomials that you can get out of Garding's work. Although we don't need anything that sophisticated. Well, okay, I shouldn't say we don't need anything that sophisticated. There are a couple ways to go with the proof. But that's our notion of an upper bound. And like this is just an example. I traced out here in blue the roots of a particular real stable polynomial of degree 4 in 2 variables. So you can sort of see what the roots look like. Okay, we are eventually going to want to set all of our variables to be the same. So I want an upper bound where all the coordinates are the same. So it should lie on the diagonal. So we want to get upper bounds on the polynomial. So to do this, let's take a look at what happens when we subtract off derivatives. We want to understand what the operation of that is. Because the original determinant that I start out with, it's very easy to understand. It's harder to get a grip on what happens when you subtract off derivatives. So if I subtract off the derivative in y, let's say, it sort of shifts the roots upwards in the y direction. This intuitively makes sense. If you actually subtracted off not the derivative in y, but like epsilon times the derivative in y, this would correspond very closely to just shifting the whole picture up by epsilon in direction y. It's just when you take something more than an infinitesimal amount times the derivative that you have to worry about what happens. And you can see that it's not just shifting it out. Like you'll see these roots actually puff out quite a bit here when we shifted it up. OK, so to keep track of this and what happens to the roots when we apply the operators, it turns out we can't just apply an upper bound. For induction, just knowing that the roots are less than something is not sufficient. We need a stronger way of measuring where the roots are. So we introduce what people in some communities call a soft maximum, or it's also related to the Cauchy transform or barrier function I used in the last lecture. Here I'll define it as what we call an alpha max. So first let me tell you what it is for a bunch of numbers. Think of these as the roots of a univariate polynomial for now. If I have numbers lambda 1 through lambda n, an alpha max, it's the number u that's larger than all the lambda i's. So the sum of 1 over u minus lambda I is equal to alpha. OK, to understand this, if alpha is infinity, this is the max. If I make alpha infinity, then u will just be the largest of the roots, and that's where it blows up. If alpha is close to infinity, if alpha is a big number, this is very close to the maximum. When alpha gets smaller, then this pushes up much more than the maximum. So the reason we look at things like this is just it behaves much better with respect to operations and is nice and continuous in ways that the maximum, well, I guess it's continuous, but the derivatives are messy. It behaves much nicer than the maximum. So one reinterpretation of one of the theorems I gave you last lecture tells you for a univariate polynomial what happens to the alpha maxes when you subtract off the derivative. So if I take a univariate polynomial, and I subtract, oh, by the way, I should say, of course, I overload this notation for a polynomial. I define the alpha max to be the alpha max of its roots. OK, if I want to subtract off the derivative of a polynomial and understand what happens to the alpha max, the theorem I gave you last lecture, you can use the same math to say it tells you the alpha max increases by at most 1 over 1 minus alpha. OK, so you might wonder why I have a 1 minus alpha in there, because I said you can have alpha be more than 1. If alpha is big, we actually can't control nicely what happens to the alpha max when you subtract off the derivative. You would need to subtract off something smaller. So the 1 here corresponds to the fact that I'm subtracting off the derivative. So if I'm subtracting off the derivative, we can control the alpha max for any alpha less than 1. And we know how much it blows up, and this theorem is basically tight. Next lecture, I'll derive something that you could derive the tightest possible theorem from, but it's basically tight. OK, so I should also mention last lecture these associated Laguerre polynomials popped up. If you want a really simple way of analyzing the roots of associated Laguerre polynomials, this theorem gives you the sharpest bound that you'll get. OK, so I'm doing this in one variable. You know we're going to need to eventually go to the multivariable case. Let me tell you the important part of the proof of the one variable case that will carry you over to the multivariable case. What we did is we defined this barrier function, which, or the Hilbert or Cauchy transform of the empirical distribution on the roots. You can write this either, say, the derivative of the polynomial divided by the polynomial, or the derivative of the log of the polynomial. All we really use in the proof of this theorem is a small algebraic manipulation, that's basically trivial, and two qualitative facts about the log of the derivative, which are that it is convex and monotone decreasing when you are above the roots. Below the roots, when you can hit singularities, bad things happen. As long as u is more than all the roots, it's convex and monotone decreasing. And those are the two facts we need. Okay. And then using that, and we'll establish a multivariable generalization of it, we can get the bound we need on the roots of the polynomial. So the way we do it is, again, we recall that the mixed characteristic polynomial has this nice formula in terms of a determinant, and then a bunch of operations where we subtract off derivatives. So what we do now is we don't just look at upper bounds on the roots. We look at what we call alpha upper bounds, which, again, are points where they're an upper bound, so there are no zeros in the quadrant rooted at them. But we also need in each coordinate, we are an alpha max. Or really, I wrote it here, it has to be at least an alpha max. Some coordinates, you could be an alpha I max, where alpha I is less than alpha. That's better. That's a better maximum. So our main theorem is that if you have an alpha upper bound on the roots, so that's really an upper bound that's pushed away from the roots in a nice way, and I subtract off the derivative in the jth variable, then I can also move forwards in direction j by 1 over 1 minus alpha, and that will be an upper bound on the roots. Okay, so the idea of this statement is if I have an upper bound, and I subtract off a derivative in the jth variable, I can get an upper bound for a new point where I've increased the jth variable a little bit. And that is what we need. So, and to prove it, again, you basically need qualitative facts about this barrier function. So the proof is a little bit of algebra, but what we need to know is if I look at the barrier function in the ith variable, that it is decreasing and convex in the jth variable above the roots. Okay, so the theorem that I told you before about one variable, it's really a statement about bivariate real stable polynomials, because we only care about a variable I and a variable j. Turns out to make this proof work and the induction work, right, what I showed you for one variable would tell me that this is convex and decreasing in the ith variable. We also need to know that the barrier function is decreasing and convex in any other variable. And as I said, it's very nice. This is just a theorem about bivariate real stable polynomials. So there's a big hammer for dealing with bivariate real stable polynomials. It's a theorem of Helton and Vinokurov, which gives you a characterization of those polynomials. It tells you that every bivariate real stable polynomial you can write as the determinant of a plus bx plus cy, where b and c are positive semi-definite matrices. And once you know this, you can, I like this because it lets you prove anything you want about the polynomial, basically, because this is really easy to deal with. So this is what we use to prove that it's decreasing and convex. If you don't want to apply to the machinery of Helton and Vinokurov, Jim Reniger pointed out to us, actually, you can get a proof out of this paper by Bauschke, Guler, Lewis, and Sendov, which was about doing optimization on real stable polynomials. And they have this order convexity results we would have needed about the barrier function. And Terry Tao went and wrote a mostly self-contained proof in his blog, which is another way to get at it. So there are a few ways to prove those facts now. The last ingredient you need in the proof, I sort of told you how we do the induction. You need to get started. You need an initial upper bound on our first polynomial, which is the determinant of this sum. And you can get that just because with the barrier function for this, which is the derivative of this in some variable, we understand by Cauchy's formula for the derivative of the determinant. And it tells you that it's just equal to the trace of the inverse of the sum of these times one of the matrices. And well, each of the, I'm doing this when all of the variables are the same, and I knew the sum of my matrices was the identity. So the sum of all of them at my initial point is t times the identity. So we know exactly what the barrier functions are when we start. And then we apply the previous argument inductively. Okay, so that is the end of the theorem. Let me just end with a few open questions and comments or other interpretations. So first, you can, if you want, interpret this probabilistically. The probabilistic interpretation would be if I have a bunch of independently chosen vectors, say with finite support, then, and if you know that the expectation of the sum of their outer products is the identity, and the expected norm of each of them is at most epsilon, sorry, that's the norm squared, then at least with some non-zero probability, the norm of the sum is at most 1 plus epsilon squared. That's a probabilistic interpretation. That proves our main theorem, which I described as there exists a partition of the set of vectors we started out into two parts, so we're both approximately half spherical. So we later figured out we can also directly prove a conjecture, or Anderson's paving conjecture, which previously you had to go through a somewhat convoluted route to get to. So Anderson's paving conjecture looks at a partition into more than two parts. But these two papers give you a way of turning into a nice statement about vectors as well. So this conjecture would consider a set of vectors where the norm squareds are at most a half. Now, actually, the half is a critical thing. The previous argument I gave you doesn't work if the norms of the vectors are at most a half. It would break. The reason you want to do something here is I was looking for a partition into two sets. Here they need a partition into many sets. And you can use the same technique, the mixed characteristic polynomials, say, OK, I don't have to partition into two parts. I can partition into many parts. And the conjecture would be that if I have a bunch of vectors, each of norm at most a half, and the sum of their outer products is the identity, then there's some fixed k that's a function of this epsilon you want to get eventually, so that you can partition into k parts, and the sums of the outer products in each part are bounded away from 1. And that gets you this initial paving conjecture I mentioned of Anderson. OK, so just one conjecture. This is what Adam and I are working on this week. I probably won't solve it, so hopefully someone else will. We think a half is a threshold for where this phenomenon exists. So Weaver's conjecture, we suspect is true. If the vectors all have norms bounded strictly below a half, we believe you should be able to partition them into two sets so that the sums of the eigenvalues in each set are bounded strictly below 1. Yeah, when it's a half, yeah, they're very easy counterexamples when it's a half. Or pretty easy. Random vectors also do it in that case. Yeah, so you shouldn't expect it when it's a half. But strictly below a half, I'm willing to bet this is true. And we also think we know what the extreme case is. Just like van der Waarden's conjecture and Bappett's conjecture, we expect that when you look at these mixed characteristic polynomials, we'd want to know which one of them has the largest maximum root, and we suspect it happens when all the matrices are multiples of the identity. In which case, you would get an associated Laguerre polynomial. And we have a lot of numerical evidence that supports this. And I know we spent way too long trying to prove it because it looked true, and it would have made the other proofs very nice. But someone will hopefully prove it one day, put us out of our misery on that. So let me end with a few questions. One, which as a computer scientist is very interesting to me, is can we compute these partitions efficiently? We have no idea. The argument I gave you here, you probably cannot do efficiently because it sort of involves computing mixed characteristic polynomials, and their low-order term is a permanent, and computing permanence is provably computationally hard. So we don't expect an efficient algorithm for this proof, but maybe a different proof you could do something with. Another question really is how good can this paving be? This is of particular interest for Anderson's paving conjecture. If I want to have each partition have roots bounded away from 1, how big does k need to be? And there are a bunch of different versions where if you get the right bounds, a lot of other interesting things happen. So, and our techniques are off by many orders of magnitude for the right paving. I mean, not orders of magnitude. If you look at the polynomials in terms of epsilon and things, they're wrong that we're getting using anything we know right now. I guess a natural question is, what else can you construct this way? OK, next lecture we'll address that a little bit. So this method of interlacing polynomials lets you construct things that you might not be able to otherwise, or at least prove that things exist. Next lecture, I'll use it to show that Ramanujan graphs exist of every degree and every number of vertices. And part of getting at that, it really seems to understand mixed characteristic polynomials, to understand constructions with interlacing polynomials, you need to understand polynomials. We need new techniques for understanding how the roots of polynomials behave and what they are. And in particular, if you look at operations on polynomials that preserve real rootedness, and you can find entire books on this topic, or just reread Poli and Sego's Problems and Theorems in Analysis, and you find a lot of that, operations that preserve real rootedness. A lot of people just talk about that qualitatively. They say, this preserves real rootedness. Almost none of these analyses have along with them an analysis of where the roots go. And suddenly this is much more interesting to me. So in the next lecture, the way we get at Ramanujan graphs is by doing such an analysis. We take operations that were classically studied 100 years ago and known to preserve real rootedness, and now we derive bounds on where the roots are, and they turn out to be nice and magical and get us Ramanujan graphs. I'll stop there. Thanks.